Ladies and gentlemen, we're from Gain University and IMEC. Today I'm gonna share one of our research. The topic is cross-modality attention and multimodal fusion transformer for pedestrian detection. Pedestrian detection is one of the important challenging tasks in computer vision because of its various applications, such as autonomous driving or video surveillance. In order to achieve more robust and accurate detection performance, thermal images has been used as the complementary information to solve the challenging problems, such as occlusions, background clutter, or adverse lighting condition in traditional RGB-based detection. In most previous methods, they are based on the two-stage detection model, such as faster RCNN, which is composed of region proposal network and the classification network. Before region proposal, the features from the two modalities, the thermal and RGB, are fused into the same feature space during the feature extraction. They only focus on how to use the fused features, or we can call them modality shared features, to perform region proposal and pedestrian detection instead of exploring the modality-specific feature extraction before the fusion process. So the modality-specific features might not be fully explored or used during the feature fusion, and with the modality shared features only, the upper bound of the discrimination ability might be limited. For example, the texture or color of RGB images in bad lighting conditions might not be properly explored due to the domination of strong signals from the other modality in fusion process. However, in conventional RGB-based detection, the texture of the object provides important cues that make the target distinct from the background clutter. So, without fully considering specific features, the fused information becomes the main discriminative cues, which limits the upper bound of discrimination ability. So, how do we entirely use the specific features in the fusion process and enhance the discrimination ability? That is the question we would like to solve in this work. Here is our proposed architecture. It is composed of three main parts. The first one is the two-string feature extractor, including the cross-modality attention transformer to cross-reference the other modality's data. The second one is the modality-specific region proposals. We use two independent region proposal networks to find the proposals in each modality. The final part is the multimodal fusion. We fuse the proposals from the two modalities based on the ROI pairs and perform the classification and bounding box prediction. For the cross-modality attention transformer, our goal is to enhance the modality-specific features by referencing the other modality's data. Two modality patches are fed into the transformer simultaneously as input, and we use the shared positional embedding to indicate the same position of different modality patches, and the output are the two independent modality-specific feature maps. In this module, we try to reference the other modality's image and enhance the features by the current modality's data to get the specific feature maps. For example, the RGB image patches will check the content of the thermal patches. If there is a person in the thermal patches, but we cannot see the person in our RGB patches, the network will try to enhance it by self-attention on the RGB data. So, the thermal data will only provide the information that where might have strong signals, but we still use the RGB data to construct the output. We do not perform feature fusion in this stage. We hope that the model will learn something from by the hint given by the other modality to enhance the modality-specific features. So, how do we achieve this goal? In traditional self-attention mechanism, all the queries will apply the dot product to all the keys to get the attention matrix, and then multiply the values to get the output. we used a similar strategy but with different attention methods to achieve our goal. In our proposed cross-modality attention mechanism, we use RGB queries to ask thermal keys to get the attention matrix, and then we use the matrix to multiply RGB's values to get output. So the thermal image will only provide the attention information instead of directly providing the data. The output is still made of RGB's own values. And we do the same thing on thermal queries, asking RGB keys to get the attention matrix and multiply thermal's value to get output. So after we get the modality-specific features from the two-string feature extractor, we use two independent region proposal network to get the ROI. And then we match the ROI from the two modalities to form the ROI pairs. Finally, we use our proposed multimodal fusion transformer to perform the fusion process and output the classification and bounding box prediction. The objective of the multimodal fusion transformer is to merge the modality-specific features from the ROI pairs. We divide the ROI pairs into patches as input. After the multimodal fusion transformer, we will get the classification and bounding box predictions according to the different tokens. So what do we achieve with this module? First of all, we improve the precision by fusing modality-specific features. The ROI pairs with modality-specific features would provide more detail than only considering the modality shared features. And second, our fusion scheme only focuses on combining each ROI pair separately instead of considering the whole feature map. So we can use different weights to combine the pairs and make the prediction, which make it more flexible. And finally, different from cross-modality attention, in order to fuse the two modality information, we use the traditional self-attention to find the attention matrix among the two modalities. Moreover, in order to learn more discriminative feature representations, we introduce content-aware laws to enforce our model to group the features based on the content. In every training batch, we calculate the average feature factor of foreground and background as two center features, and then we shorten the distance between all the foreground samples and the center foreground features. Also, we shorten the distance between all the background samples and the center background features to make sure the features with same labels much closer. In addition, we expand the distance between the foreground and background center features to encourage the model to learn more distinguishable feature representations. In all the experiments, we use log average miss rate as our metrics to evaluate the detection performance. A lower miss rate score indicates better performance. So, in the first experiment, we used the KAIST dataset to evaluate the detection performance. This dataset consists of 95,000 RGB thermal image pairs. We compare with other competitors with similar feature extractors. Our method can achieve better performance no matter in day, night, or all the subsets. We did the same experiment on the CVC14 dataset. This dataset is smaller and the RGB thermal pairs are not synchronized properly, which make this experiment more challenging. We still compare the performance with the others. Our performance can achieve better performance in every subsets. So, after the quantitative results, we conduct some implementation studies to show the effectiveness of our method. We can see that in the D column, our model can pay attention to the pedestrians properly with our cross-modality attention transformer, and there are also more detection results when applying the cross-modality attention transformer. In conclusions, in this work, we have identified the disadvantages of the recent methods, which relied on modality shared features for multimodal pedestrian detection, and introduced a new modality fusion scheme. We proposed the cross-modality attention transformer, which identifies related features in both modalities and consults the second modality in order to perform information aggregation. Furthermore, our proposed multimodal fusion transformer performs association between detected regions in a more efficient way compared to classical CNN methods. In our experiment, we verified the performance of our model against recent relevant methods and achieved comparable or a better detection results on the KAIST and CVC14 datasets. And here is the reference page. Thank you.